In a quiet industrial complex on the outskirts of a coastal city in the United States, dozens of trucks roll in every morning carrying a cargo no one wants to talk about: rotting fish. These are not the pristine fillets seen in supermarkets or the fresh catch unloaded at high-end seafood markets. These are the rejects, unsold inventory from fishmongers, byproducts from processing plants, fish too damaged, expired, or contaminated to make it to a consumer's plate. Some are intact, others are partial remains: heads, bones, viscera, skin, all slowly decomposing. The smell is overwhelming, acidic, and sharp. But to the people working inside the factory, this waste is not a problem. It's potential. Because behind these walls, rotting fish are transformed into something vital: fertilizer that nourishes millions of acres of farmland across the country. The process begins the moment the fish waste is offloaded. It's not dumped blindly into a pile. Instead, it's sorted by source and composition. Whole carcasses go one way, high-fat byproducts another, and heavily contaminated waste to a separate treatment line. Workers in thick rubber suits and face shields maneuver the piles using hydraulic lifters and floor scrapers. Everything is weighed, logged, and sampled. Why? Because not all fish rot the same. Oily fish like mackerel or sardines break down faster and release more ammonia, while lean fish like cod decay slowly but have better protein recovery. Understanding the biochemical profile of each load helps the plant control pH levels, nitrogen concentration, and pathogen risk. The fish waste is not treated as garbage. It's handled like a raw material. From there, the journey into transformation begins. The first major step is grinding. Massive metal grinders with rotating blades tear through bones and flesh, reducing everything to a thick, pasty slurry. The mixture is heated slightly, not enough to cook it, but just enough to loosen muscle fibers and activate bacterial breakdown. It's then piped into enormous sealed vats known as hydrolysis tanks. These tanks operate under controlled pressure and temperature, where enzymes, both naturally occurring and added, accelerate the decomposition process. Within 24 hours, the chunky mixture becomes a uniform liquid teeming with amino acids, peptides, and fatty acids. This stage is crucial, as it defines the nutritional profile of the final fertilizer product. The liquid is now called fish hydrolysate. Meanwhile, gas scrubbers installed above the tanks extract foul-smelling compounds like hydrogen sulfide and methane. These are captured, filtered, and often repurposed as low-grade energy sources for the facility itself. Nothing is wasted. The bones and scales that resist breakdown are separated via centrifuge and redirected to be dried and milled into fish bone meal, a powdered additive rich in calcium and phosphorus. The remaining oil floating on top of the hydrolysate is skimmed, filtered, and sold separately to be used in animal feed, biodiesel production, or even cosmetics. Every molecule of decay is redirected into a purpose. Once the hydrolysate is fully processed, it's stabilized with food-grade acid to bring the pH down, usually to around 3.5. This prevents further microbial activity and ensures safe storage. It's then pumped into stainless steel holding tanks where it's tested rigorously. Bacteria counts, nutrient density, heavy metal content, and viscosity are all checked against standards. Only batches that meet strict criteria are approved for bottling or bulk delivery. The final product looks like dark brown syrup and smells exactly like what it came from, but in the agricultural world, it's liquid gold. Farmers across the country rely on it for organic crop production, especially those growing vegetables, fruit trees, and specialty grains. It provides nitrogen, potassium, micronutrients, and soil-enhancing enzymes in a way that synthetic fertilizers often can't match. The factory floor is a testament to controlled chaos. Workers in waterproof gear move constantly between stations, adjusting temperatures, checking gauges, flushing pipes. The air is thick with steam and the sharp tang of fermented protein. Forklifts move large totes of finished product toward loading bays while automated pumps fill 55-gallon drums destined for farms in California, Texas, and Florida. On a good day, the facility can process over 60 tons of fish waste, turning what would otherwise be landfill material into nearly 40,000 gallons of market-ready organic fertilizer. It's an operation that blends biology, chemistry, and logistics into something few ever think about: But that touches almost every table in the country in the form of food grown with nutrients reclaimed from what was once considered trash. Outside the facility, the logistics of collecting and transporting fish waste are just as critical as what happens inside. Most of the raw material comes from seafood distributors, grocery store chains, and fish processing plants located along the eastern and Gulf coasts. Contracts are established not based on volume alone, but on consistency, handling practices, and geographic reach. Every morning before sunrise, refrigerated trucks depart from partnered suppliers, carrying totes filled with waste material sealed in thick polyethylene liners. Unlike fresh seafood trucks, these don't operate on ice, but on containment and timing. If the waste degrades too far during transport, the enzyme balance shifts, ammonia spikes, and the hydrolysate process becomes unstable. Drivers are trained to check for bloating, discoloration, and foul odors before unloading. Any load that shows signs of anaerobic decay beyond acceptable thresholds is rejected on the spot and redirected to lower-grade rendering plants that don't produce fertilizer. Quality control starts on the road. The volume is staggering. One mid-size facility can receive up to 100 tons of fish waste per week, enough to fill several semi-trailers end to end. And this is just a fraction of the waste generated nationally. According to recent data from the NOAA and USDA, over 2 billion pounds of seafood byproducts are discarded each year in the United States. That includes bones, heads, skin, and unusable flesh from everything ranging from tilapia and salmon to squid and shellfish. Only a small percentage is reclaimed through operations like this, but that percentage is growing steadily. In part, it's driven by the surge in demand for organic fertilizers. As consumers push for food grown without synthetic chemicals, farmers look for nutrient-rich alternatives. Fish hydrolysate fits perfectly into that demand: organic, renewable, high in bioavailable nutrients, and certified by many organic farming boards. Once the processed fertilizer leaves the factory, it enters a second supply chain, one just as intricate as the first. Some of it is bottled and labeled under national brands and sold in garden centers, while the bulk is shipped in bulk to agricultural distributors who blend it into custom formulations. In states like California and Oregon, large-scale vineyards and organic farms apply thousands of gallons per season, delivered by tanker trucks with direct injection into irrigation systems. These fertilizers are often combined with kelp extract, molasses, or humic acids to improve soil retention and microbial health. Because fish hydrolysate is absorbed more slowly than synthetic nitrogen, it supports long-term soil structure while feeding plants gradually. That's especially valuable in high-value crops like berries, leafy greens, and orchard trees, where nutrient balance directly impacts flavor and yield. The environmental benefits are also notable. Unlike traditional rendering, which often involves high-temperature cooking and produces significant emissions, hydrolysate processing is a low-heat, low-energy method. It produces less CO2, and because nearly every byproduct is repurposed, it drastically reduces landfill waste. Some facilities have even partnered with local utilities to feed excess methane into microturbines that power sections of the plant. Others donate leftover bone meal to community gardens and soil restoration programs. In coastal areas where fish waste once clogged landfills or was dumped into waterways, this approach has turned a disposal problem into a closed-loop system, benefiting both farms and fisheries. Inside the control room of the factory, technicians monitor live data from each stage of the process. Digital dashboards show enzyme activity curves, tank pressures, oxygen levels, and pump rates. Cameras feed real-time video from grinding bays and holding tanks, allowing supervisors to spot foam buildup, sediment blockages, or temperature anomalies. If anything deviates from the safe range, alarms trigger automated overrides and dispatch floor teams. In a system where the material is actively decomposing and microbial activity is constantly changing, vigilance is non-negotiable. Each batch is treated like a living system, monitored, adjusted, and stabilized before it ever reaches a farmer's field. Yet, for all the technology and structure, the work remains physically demanding. Workers endure long hours in wet environments, handling hoses, valves, and heavy drums while navigating slick floors and pungent air. They wear full-body protective suits, face shields, and respirators in certain areas, not just because of odor, but due to aerosolized proteins that can irritate the lungs. Still, turnover is low. Many employees stay for years, drawn by a sense of purpose. They see their role as part of something bigger, taking waste that once meant cost and contamination, and turning it into life-sustaining nutrition for soil. That sense of contribution fuels the efficiency and pride that defines every shift. The final moments before shipment involve meticulous inspection. Quality control staff take random samples from bulk tanks, testing not just nutrient levels but pH stability, microbial safety, and visual clarity. If a batch fails, it's recirculated, retreated, or blended with stabilizers until it meets spec. Only then is it cleared to be pumped into drums, loaded by forklift, and secured for delivery. On the shipping dock, pallets of fish-based fertilizer stand wrapped in plastic, labeled by batch number and destination. Some are headed to organic farms in Florida, others to urban gardens in Detroit, and a few to rooftop greenhouses in New York City. From rot to rows of produce, the journey of this material defies its origin. But to those who run the operation, it's not magic, it's just biology, harnessed and directed with precision. Long before the trucks arrive, the process actually begins at the supplier level, where grocery stores, seafood distributors, and processing plants must manage their own waste in a way that aligns with strict requirements set by the receiving factories. Fish that are expired, unsold, or left over from filleting operations must be handled carefully to preserve the integrity of the material. Storage is key. These suppliers keep the waste in cooled, sealed bins to slow down anaerobic decomposition, ensuring that bacteria and pathogens don't overwhelm the biological balance needed for hydrolysis. Every bin is tagged with a barcode containing its source, date, fish species, and storage time. When pickup is scheduled, this information is transmitted to the factory's database, allowing the lab team to prepare enzyme blends in advance. Because every type of fish decomposes differently, blending enzymes properly ensures efficiency once the load arrives. Even before the waste is touched, the system is already optimizing for the end result. Once the material arrives at the facility, it's not just dumped and processed, it's tracked. The factory operates on a batch traceability model, where each incoming load is matched with a batch ID and digitally followed through every phase of transformation. That means from the moment a box of unsold mackerel is emptied into the grinder, its origin, weight, and breakdown progress are recorded in real time. This allows the facility to generate compliance reports for regulatory agencies, provide documentation to organic certifiers, and resolve any downstream quality issues. If, for instance, a batch is later found to have off odors or unusual mineral content, the system can trace it back to the exact source, temperature at arrival, enzyme recipe used, and tank rotation cycle. This traceability is what makes the operation not just efficient, but legally and commercially viable on a national scale. As the hydrolysate ferments, factory engineers constantly adjust parameters to maximize nutrient retention. Certain enzyme blends are used to preserve amino acid profiles, while others break down stubborn tissue structures. Some tanks include microaeration systems that inject tiny amounts of oxygen to support beneficial bacteria, preventing the growth of sulfur-producing microbes. Throughout the process, samples are extracted using sterile nozzles and tested in an adjacent lab equipped with spectrophotometers, microbial incubators, and precision pH monitors. The lab doesn't just check for safety, it fine-tunes the product's agronomic value. Nitrogen levels too low. More time in the tank. Viscosity too high. Add water and adjust agitation rate. The product is dynamic, and the factory treats it like an evolving substance, not a static one. Next door, the bone meal line operates in parallel. After grinding and separating solid particles, these fragments are fed into rotary dryers, massive cylindrical drums spinning slowly under gas burners. As they tumble, the moisture evaporates, leaving behind a dry, powdery residue that's rich in phosphorus and calcium. Once cooled, the bone meal is passed through sieves to eliminate larger fragments, then bagged in 25 or 50-pound sacks. These are sold directly to farms, landscaping companies, or wholesale garden centers. Unlike the hydrolysate, bone meal is dry and shelf-stable, making it easier to store and ship in bulk. Some high-end brands even add mycorrhizal fungi and trace minerals, marketing it as a premium organic soil amendment for fruit trees and perennials. It's another way the facility ensures that every ounce of waste finds a destination. The oil extracted during hydrolysis also finds life beyond the factory. While unsuitable for human consumption due to oxidation and trace decomposition compounds, it's still valuable. Some of it is sold to feed manufacturers who blend it into poultry or aquaculture diets. Other batches go to biodiesel producers who convert it into low-grade fuel used in farm machinery. And a growing number of cosmetic startups are experimenting with fish oil derivatives for skin creams and natural emollients. Though less glamorous than essential oils, the omega-rich composition of refined fish oil makes it useful when filtered correctly. These downstream markets offer secondary revenue streams for the factory while helping reduce overall waste footprint. But perhaps the most surprising part of the entire operation is its economic efficiency. By processing a product that most suppliers would otherwise pay to dispose of, the factory creates a rare economic inversion. It earns money from both ends of the supply chain. Suppliers offload their waste at little to no cost, while farmers, distributors, and manufacturers pay for the final products. It's a closed-loop system where logistics and biology intersect with economics in a way that benefits everyone involved. Local governments support these operations because they reduce landfill pressure. Farmers support them because the product is reliable, renewable, and accepted in organic agriculture. And the public, unknowingly, supports it every time they bite into a tomato, a lettuce leaf, or a berry grown with fish-based fertilizer, never realizing the complex network of tanks, grinders, enzymes, and workers that made it all possible. There's also a cultural side to this practice. In many coastal communities, where fishing has been a way of life for generations, seeing fish waste turned into fertilizer is more than innovation, it's continuity. It reflects an old idea made new, that nothing taken from the ocean should go to waste. What once fed the land in small garden patches now fertilizes entire agricultural regions, closing a loop between sea and soil. It's not just an industry, it's a philosophy of stewardship built into steel tanks, shipping schedules, and safety protocols. It's why, even as technology evolves and markets shift, these factories remain deeply connected to place, people, and purpose. As the demand for sustainable agriculture continues to rise, the role of fish waste processing facilities is expanding far beyond what their founders originally envisioned. What began as a solution to a disposal problem has become a cornerstone of the circular economy, where biological waste streams are not only managed, but monetized and reintegrated into food systems. Across the country, similar facilities are being proposed in port cities and fishery hubs, from the Pacific Northwest to the Gulf Coast. These new sites aim to replicate the success of the pioneers by building modular hydrolysis units, upgrading wastewater treatment systems, and securing long-term partnerships with local seafood processors. But as the network grows, so do the challenges. Consistency of input remains a hurdle. Different species, handling methods, and environmental conditions can all affect the efficiency of conversion. To address this, factories have begun developing AI-assisted quality control systems that use visual sensors and microbial data to categorize incoming waste in real time and assign it to optimal processing streams. The integration of artificial intelligence with biological processing is turning waste management into a high-tech frontier. Out on the farms, the results are tangible. Growers who once relied on synthetic nitrogen are seeing the benefits of fish-based fertilizers firsthand: improved soil structure, better water retention, higher microbial activity, and increased crop resilience during drought or heat stress. Some farmers report richer flavors and longer shelf life in fruits and vegetables grown with hydrolysate, especially in tomatoes, strawberries, and leafy greens. Others highlight how the fertilizer's slow-release properties reduce nutrient runoff, a major environmental concern in many agricultural regions. Unlike chemical inputs that leach into rivers and groundwater, fish hydrolysate binds to soil particles, delivering nutrition more gradually and sustainably. For organic farms, the product offers something even more valuable: certification-compliant input that supports yield without compromising ecological standards. In this way, fish waste, once discarded in heaps behind fish markets, is now playing a role in transforming how food is grown across America. The factories themselves have also evolved. In recent years, some operations have expanded into education and community outreach, hosting tours for students, researchers, and policymakers interested in waste-to-resource innovation. Visitors are often surprised to discover just how sophisticated the process is. How many sensors, lab protocols, and logistical frameworks are required to turn something rotten into something regenerative. Others leave with a new understanding of the scale of food waste in modern supply chains. These tours are not just PR, they're part of a broader shift toward transparency and awareness. By opening their doors, these companies challenge the stigma around waste and invite the public to see value where once there was only disposal. This cultural shift is essential if circular systems are to thrive, because sustainability isn't just about technology, it's about perception, policy, and participation. Back in the control room, operators continue their work with quiet precision. Pumps hum, data updates on screen, and a new shipment of fish waste is already backing into the unloading bay. The day's cycle repeats: measure, grind, heat, convert, stabilize, test, ship. The product may be invisible in the final food chain, but its effects ripple outward, from richer harvests and healthier soil to reduced landfill pressure and cleaner coastlines. And for the people inside the factory, that's more than enough reward. Many of them began as laborers, trained on the job to understand biochemistry, logistics, and regulatory frameworks. Now, they're proud stewards of a system that embodies both efficiency and ecology. They don't see waste, they see possibility. In their hands, a rotting fish isn't the end of a story, it's the beginning of another. From the ocean to the farmland, this journey represents more than a supply chain. It's a connection between industries, environments, and people. A forgotten fish in a dumpster becomes nitrogen in a strawberry, calcium in an apple tree, or potassium in a field of lettuce. It travels silently across states, inside unmarked drums and anonymous hoses, but leaves a powerful trace wherever it goes. And while most consumers will never know where their food drew its strength from, the truth is buried deep in the soil, fed by the unseen work of machines, microbes, and humans who believe that nothing should be wasted. Not even a fish that no one wanted.